wait till it. She's good at this. Just wait.
Perfect.
All right, everybody can see that, right?
Yep, we're good.
All right, so this is number 1 from 11.7.
Nice.
Right, now I looked at this, and what I don't like about it is, gosh, it's got the -1 and the 1.
Mm-hmm.
Right, and it doesn't reduce, so you couldn't say that's just 1 over n, because this would be, like, if these weren't here, you could reduce this to what? 1 over n?
Yeah.
Okay, so when I see something like that, I think to myself, oh gosh, oh, I wish it was 1 over n. Because I know what 1 over n is doing.
Yeah.
Okay, and so I would use something called the limit comparison test. Have you heard of that?
Yeah.
Okay, so the limit comparison test states if you find the limit as n goes to infinity here of something you'd like to compare it to. So I'm going to compare it to. Now, how did I choose the sequence n equals 1 to infinity of 1 over n? How did I come up with that? I said, well, I wish that wasn't there, and I could say that it's 1 over n. Everybody agree?
Yes.
Okay, so the limit comparisons test says that these will behave the same if you take the limit as n goes to infinity if they come out with a number that's the limit that is a number, you know, like 1 or 2 or 7 or 1/2. That means it behaves the same as you go to infinity. Okay, and so it will either converge or both diverge. And we know that this one diverges. So let's just see what happens. All right, so what I'm going to do is I'm going to put the 1 over n on the bottom because it's a nicer one to keep, change, flip.
Mm-hmm.
And then here we go. We're going to go n squared minus 1 over n cubed plus 1. And then I can say the limit as n goes to infinity of n squared minus 1 over n cubed plus 1 times n over 1. So what happens when you multiply that in? You know, it would be what? N cubed minus n over n cubed plus 1. Now, I don't know, Mackenzie, if your professor is okay with you guys, doing n behavior limits with just covering up and just looking at the highest exponents like we used to do.
Yeah, he is.
So these aren't going to matter much. When I say these, I shouldn't say these. These aren't going to matter much as you go to infinity compared to these.
Right.
Okay, because a million cubed next to minus a million is huge. So these start meaning less and less. So what is this limit approach? This limit approach is
1.
1. Okay, so that means at infinity, these two characters are going to behave the same. Which means since this diverges, so does this.
Oh. Okay, so if you do the limit comparison test and you get it to be a number, then they both do the same thing.
Yes.
So if you know what the easy function does, you know what the hard one does because they're the same.
Yep, they behave the same at infinity, yes.
Gotcha.
Okay. Now,
but when you do this test, it has to come out to a number.
Now, what do I mean by not a number? For example, if this were to turn out to be infinity or negative infinity or 0. A 0 is a number, but that means if it goes to 0, that meant the 1 on the bottom grew faster, which doesn't help.
It doesn't help you at all. You need it to be something that is not 0 or plus or minus infinity.
Right. It has to be a number, yes.
Okay.
What are some other things that besides 1 over n that we could use to compare it to?
Yeah. So what else? Like, what are some functions like series that we know what they do? Like the P series, like any like the P1?
P series. Okay, so let's talk about that.
Okay.
Siri just thought I said something to her. That was hilarious. Okay. So the P series, n equals 1 to infinity of 1 over n to the P. And of course, they call it a P series because the exponent is a P. I know it sounds silly, right? But if So if P is equal to 1, that's the harmonic series. And we know that diverges by the integral test. I mean, if you had to prove it to somebody, because you can integrate 1 over x here, you know, I'd use the integral test if I had to prove that diverges. Anyway, if P is greater than or equal to 1, it diverges. I mean, I'm sorry, let's try that again. Just remember, it's 929.
Yes.
Okay, so if P is, greater than 1, it converges. Because think about it. What happens if this is 2, 1 over n squared? If you were to integrate 1 over x squared dx, that's equal to negative 1 over x.
Mm-hmm.
And this is going to go to 0, isn't it?
Yeah.
And so so anything that has an exponent that's greater than 1 is going to be a decreasing function basically when you're done integrating it. So that's why it converges. So P series with P greater than 1 will converge. You can add them up.
Okay.
P. Okay. I'm sorry, I heard a question. What was that?
Oh, there was just an epiphany.
Oh,
Yes, we're realizing things.
I like those. Those are fun.
We're actually understanding, like, he said words that made no sense at the time, but like now that you're explaining it, it makes sense.
Well, that makes my heart sing. All right, here we go. So P then is less than or equal to 1. Now I'm going to include 1 here because it includes the harmonic. Then we diverge. And I'll give you a reason why. Because the integral of 1 over x dx, if you were to integrate that, is natural log of the absolute value of x. Now, natural log, if you think about what that function is, it increases, doesn't it? And so you can't add them up because the terms are constantly increasing.
Yeah.
Okay, so that's why that works. Okay. So P series is something that's wonderful to compare to.
Yes.
I mean, if I'm doing the limit comparison test, I'm usually doing it with P series if I had to think about it.
Okay.
So what would something look like that you would compare to a P series test?
Like this. Like I would say to myself, oh, I wish those ones weren't there.
So if it's something where you could easily like cancel stuff if there wasn't like a number after the n.
Right. I'm going to look at some of these others ones in 11.7. Let me see. Like, okay, on number 2, does everybody see number 2? I'm going to put my phone here. Can you see number 2?
Yeah.
Yeah.
Right. But this is for those who might want to go back and watch it and they don't have their book with them. Okay.
Yes.
All right. So right here I have, oh, I wish those ones weren't here, but if I were to reduce this, what would I get? You would get
1 over n squared.
That's what I would compare it to. Do you see how that works?
Yeah. Oh, this makes so much more sense. Okay.
Okay.
Yeah.
Let's see. Number 3. Number 3 is alternating. How do I know that? Because I have this negative 1 to the n term. Okay. So I would compare this. Well, first of all, you got to do the alternating series test. Have you heard of that?
We have. We could use some any of these tests. We could use a crash course in.
All right. So
exactly.
All right. So, well, hold on. Let me see if I can find any more on this list here. That's alternating. All right. So this one here is interesting. Number 5. If you had to compare how fast e to the n grows versus n squared, which do you think would grow faster?
The exponential.
Probably yeah.
The exponential grows infinitely faster. It sure does. So this is going to, in my opinion, diverge because this is going to rocket off to infinity. Now, how would you prove that? I would probably do the integral test, which looks uncomfortable. And you'd have to integrate that by parts.
Yeah. Gross.
We don't have to do integration parts, like that's possible.
Yeah, we can do it.
Well, but now I'm thinking about it though. Can you do the integral test if these terms aren't positive? And to use the integral test, there are 3 conditions. You have to be positive terms. Well, guess what? Those are all positive. Then you have to be continuous, meaning from 1 to infinity, e to the x over x squared has to be continuous, which is true. And then it has to be decreasing, which it is not. So we can't use the integral test for that.
Wait, so the 3 conditions, it has to be positive.
I'll write it down. I'll write it down.
Increasing.
Continuous.
And okay.
Conditions for the integral test. The terms have to be, or wait, I'm sorry. F of x, which would be the function you'd be integrating. F of x has to be greater than 0. F of x has to be continuous. And f of x has to be decreased. And in this case, number 5 is certainly not increasing. Oh, I know what I would do with number 5. All right, let's talk about it. Just took me a minute to think about it.
Okay.
All right, let's do number 5 real quick because it's interesting.
Mm-hmm.
All right, let's see here, number 5, which, you really should use this test first, honestly, because it's called the end-term test for divergence.
Okay.
I didn't know why I didn't slap Mike in the face right away, but divergence. Have you told him I can't spell?
Yeah. Spelling and what, mental math on demand?
That's right.
Not your
No, they're not my thing. But I can communicate, which is more important, right?
And you can teach us how to do series, which
Right.
is
Okay, so the end-term test for divergence is simply if you have positive terms here. If you have n equals 1 to infinity, and this can be any constant down here, it doesn't have to be 1, but this one has a 1, so I'm putting a 1 here.
okay.
A sub n, what is a sub n? Well, a sub n is just this. Okay, what you're going to do is you're going to take the limit as n goes to infinity of a sub n. Okay, and if it's not equal to 0, that means your series will diverge, and you're done.
So would you recommend, unless like something like the comparison test jumps out at us, start with that test?
I'm going to go back to this one really quickly. You'll notice here, right, that if I were in my mind taking the limit as that goes to 0 infinity, what happens? The degree of the numerator it's going to go to 0, isn't it?
0, yeah.
Okay, which is, so this would be the first bullet point for the nth-term test for divergence. So if your limit is not equal to 0, then your series diverges. If the limit as n goes to infinity of a sub n is equal to 0, your test is sadly inconclusive. And so you got to move on. Do you know what I mean?
Yeah.
But in this case, you could say the limit as n goes to infinity of e to the n over n squared is infinity, right? Which is not 0. So this one diverges by the nth-term test for divergence.
Yes.
Okay, and that's really the first test you should try because this is the nth-term test for divergence, and that's the only thing it's a test for is for diverging. It's not for converging at all because it won't tell you whether it converges or not. It'll just tell you if it diverges if the limit is other than 0.
Uh-huh.
Does that make sense?
Yeah.
And what led me to that conclusion was I figured that this grew faster than this one. So I knew that these terms were going to rocket off into space.
Gotcha.
All right, so that was number 5. Let's look at number 6.
What it could be. Like being multiple choice.
176.
I'm sorry?
Number 6.
Number
We're
6.
just trying to get, yeah.
Okay, so number 6. Now, I don't know if your professor talked to you at all about the root test.
We have,
You spent like 30 seconds on it.
yeah, we maybe dusted over it.
Okay, so the root test is kind of like the ratio test. Now, what would lead me to be doing this? Well, because both of these are raised to some form of the n,
Yep.
right? I'm sorry, I'm going to put this up here. Okay, so if I were going to look at this one, I would say n equals 1 to infinity of n to the second over 1 plus n to the third, all raised to the n. Do you agree that I can do that mathematically?
Yeah.
Okay, so that's when I would use the root test,
Okay.
because both are being raised to the n, and it would be really obnoxious to have to deal with both of these to the n. Of course, you could always use the ratio test, but when this to me is pretty obviously the root test. So what is the root test? The root test is the limit as n goes to infinity of the nth root of something. I'm going to put a sub n in here. Okay, if it's equal to 1, it's inconclusive. Can I spell conclusive? Not at this hour. Okay, and then you're crying because you got to go to another test, right?
Yep.
If it's less than 1, which would be nice, then it converges. Okay, and if it's greater than 1, it diverges. Okay, now why is 1 such a special number here? Because I don't know if you guys remember when you're doing series, if you have an r that's absolute value of r is less than 1 for a geometric series, you know, like if your r is 1/3 or negative 1/3, that will converge. If it's outside of this, range, it won't. Okay, but anyway, that might be a subject for Taylor polynomials a little bit later. But okay, so let's take the nth root test here. So we say the limit then as n goes to infinity of the nth root. What is the nth root of this?
It's just that, it's just the n squared and the 1 plus n.
Right.
Cubed.
See how nice I'm going to raise this to the n because they cancel out here. And so I get the limit then as n goes to infinity of n squared over 1 plus n quantity cubed. And then we're going to do our, n behavior limits here, Mackenzie, right? What's the degree of the numerator? It's 2.
2.
The degree of the
And then
denominator is
3.
3. So this is going to go to 0. So then this one's going to converge since this is less than 1 by the root test. Now, I believe the ratio test would work also on this, but to me, that's kind of what stuck out.
Ms. Muller, can you go over your trick for doing limits for everybody that didn't have you?
Sure. Okay.
Because that makes it so much simpler.
All right, here's my, if you have a rational function, now what do I mean by rational function? That means I have f of x equals, I don't know. I'm going to give 3 examples, right, Mackenzie? That'd probably be a good idea.
Yeah.
All right, so let's say I have 1 over x, and then let's say I have f of x equals x plus 1 over x minus 2, and then I have f of x equals x squared plus x over x minus 3, okay? If I find the limit as x goes to infinity here, what happens of 1 over x? What happens when x gets really, really large here?
Goes to 0.
Goes to 0, you're right. But what is the degree of the numerator here? It's really degree 0, right? Because I don't have an exponent.
Yeah.
right?
Mm-hmm.
So if the degree of the numerator, oh, can I spell degree? No. Degree of the numerator is less than the degree of the denom, then the limit's equal to 0. Okay, because that means the denominator is going to be growing faster. What about this case? Well, if I were to take the limit here as x goes to infinity of x plus 1, actually I'm going to make this a 2x on the bottom. That'll make it more interesting. Minus 2. The degree of the numerator here is 1, and the degree of the denominator is also 1. But when I put a very large number in, like 1,000,000, this 1 is saying, well, I don't feel very big here. And this -2 is feeling very small as well. So it's almost as if they aren't there. And what do you get when you simplify this? You get
1/2.
1/2. Okay, so this is 1/2. So if the degree of the numerator, I'm starting to abbreviate, is equal to the degree of the denominator, then it's going to be a over b. Now, what do I mean by that? I mean the coefficient of the x's is your limit. So this would be like 1 over 2, right? If your f of x is equal to a x to the m, where m is the highest, over b x to the n, where n is the highest exponent in the numerator and the denominator. So your end behavior limit would just be a over b. And in this case, the degree of the numerator here is clearly bigger than the degree of the denominator. So which one's growing faster? It's going to be, well, I shouldn't say faster. These two aren't going to matter much. And then what are you left with? You're left with x squared over x, which is
Infinity.
x, right? And it's going to behave like x. It's going to behave like y equals x when x gets really large. And where is that always headed? It's to infinity. So if the degree of the numerator is bigger than the degree of the denominator, then you're going to go to plus or minus infinity depending upon whether you have a negative in front of one of these, you know? Okay? I'm going with n's here.
Yeah, so Cody, there's none of that weird divide by the highest.
That is so.
There's none of that. It's literally you just look at this, and this is like a 5-second way. Yeah.
That is so good.
Right, but now the dividing by the highest exponent is important if you want to prove it algebraically.
Yeah,
You know,
but we never have to do that. We're just looking for like a quick way to find the limit.
But that's how you do it quickly.
Which is that.
Okay.
No problem.
Yep.
Thank you.
You're welcome. Okay. All right. So when do you know whether to use the root test? When they are both raised kind of to the n here, right? And you can, and you can take it and, break it apart. All right, let's look at number 7. All right, now on number 7, I look at this and I say to myself, well, I can find the integral of that. Now, why can I find the integral of that?
Because natural logs are pretty easy.
Okay, well, what is natural log's derivative?
1 over x.
1 over the absolute value of.
So you can use u sub here.
Oh yes, yeah, because then you can cancel out the 1 over n.
That's right. So here we go. I'm going to do number 7.
Okay. Yeah.
All right, so that's going to be 1 over n square root of ln n. Now, the terms are going to be decreasing, first of all. Do you agree with that? Because I'm 1 over something. So the terms are getting smaller, right? Because what are the conditions I said over here? F of x has to be greater than 0. Well, these will all be positive. F of x has to be continuous. Well, this is going to have issues at 1 because the log of 1 is 0. So I can't have n be 1 or 0. So it's continuous from 2 forward. That's okay. and it has to be decreasing. Well, of course it would be decreasing because these numbers are getting bigger and one is staying the same. Does that make sense?
Yep.
Yes.
All right, so I'm going to say using the integral test. I should use a capital. All right, so I would say the integral from 2 to infinity is 1 over x square root of natural log of x dx, which makes this integral improper because I have an infinity here. All right, so I'm going to find the limit then as b goes to infinity of the integral from 2 to b, which somehow makes it better, which I think is hilarious. But you know, you're like, okay, well, maybe it makes it better, but it's still gross. Okay, dx, everybody agree with that?
Mm-hmm.
All right, I'm stripping my page down. All right, now I'm going to do what I call an integration aside, which means I'm going to take this over here and integrate it. Okay, which means I'm going to use u sub, and I'm going to make this ln x to the 1/2, if that's all right with everybody. So let's let u equal natural log of x. Du is what? 1 over x dx. Everybody agree?
Yep.
So then we get the integral then. Oh, that is being weird. Okay, so then we get the integral of u to the negative 1/2 du, because this becomes 1 over u to the 1/2, and this is my du.
Mm-hmm.
And then the antiderivative of u to the negative 1/2 is 2u to the 1/2, right? Because you raise the power 1, divide by 1/2, which is the same as multiplying by 2. And so then you get 2 square root of natural log of x. Right, I just replaced the u. I don't think this one's going to converge. Fascinating. Okay, so let's see. The limit as b goes to infinity of 2 natural log of x, such that we go from 2 to b. The limit as b goes to infinity of 2 natural log of b minus 2 root natural log of 2. Now what happens to this?
Natural log of infinity is
That goes to infinity.
infinities.
So this
Yes.
blows up, what I say. This blows up and goes to infinity, therefore diverges by the integral test. Now, how do we know? How did I know? This is increasing. That's how I knew it was going to diverge. Does that make sense?
Yeah.
It's because you can't come to an actual limit, right? The limit doesn't exist.
The limit, well, okay, so this is the area under the curve, okay? And so this is saying I can't add up the area under the curve because it keeps getting bigger.
Yes.
And what is series all about? Well, can I add up all these numbers and get a number?
Yeah.
And well, here this is saying no, because this is going to keep getting bigger and bigger and bigger, and I can't add it up.
Yes.
So what values would give you convergence by integral test?
If you would find the antiderivative and you had a decreasing function here.
Okay.
And then would that give you?
Because what would happen is if you had a decreasing function here, this would not go to infinity.
Right. So if you got the limit to be an actual number, like
that means it converges.
So it only diverges if it's infinity or negative infinity.
Yes, sir.
Oh, okay. Got it. Oh.
Yep. Now, how did I know I was going to use the integral test? Mackenzie, do you know?
Other than it just looks like an easy
Integral. Yeah.
integral.
Yes.
You won't even see its derivative in there, so you know it's
Yeah.
cancel
So
out.
like you wouldn't have to do any real hard work to make that integral work.
Right.
Okay.
So sometimes you can use more than one test for these, but you want to find the one that's the easiest kind of looking.
Yes, that's what I'm trying to do, is guide you to the easiest one.
Okay.
Oh, okay.
You know, and I'm telling you, that's the only way I would do this one.
Okay.
Okay, so let's see what number 8 says.
Gotcha.
Okay, this is alternating. So I would probably use the alternating series test, but what do you guys think about this? Tell me what you're thinking.
The bottom one increases a lot faster.
That's right. So this limit is going to go to 0, and it's alternating. So let's talk about the alternating series test, shall we?
Yeah, let's do that.
Okay, so what do we got here? N equals 1 to infinity of -1 to the n minus 1, n to the 4th over 4 to the n. Okay, since this is an alternating series, we're going to use the alternating series test. Now, I don't know if this abbreviation will work for you guys, but it works for the AP people.
That's fine.
Sure.
We can work with that.
All right, so for the alternating series test, there are 2 conditions that have to be met. The first one is the limit as n goes to infinity of absolute value of a sub n has to go to 0. So let's check that out. You notice I put absolute value bars. That means, do I care about this? The answer is no. Okay, so let's do that part. The limit then as n goes to infinity of n to the 4th over 4 to the n. Well, we know what this is, right? I mean, we could use L'Hopital 4 times, and this is going to go away to 0, isn't it?
Mm-hmm.
This is going to go to 0. Everybody agree with that? This is just going to grow so fast that this gets, you know.
Yeah.
So
That
that's a check. So that's the first condition, is that the terms have to be, the nth term has to be approaching 0 as n goes to infinity. So that's a good thing.
Yeah.
And then a sub n plus 1 has to be less than or equal to a sub n. Now, what does that mean? That means the terms have to be getting smaller, because this is the n plus 1th term, and this is the nth term. So the terms, like if I were going to do a sub 1, a sub 2, a sub 3, right? These would be my terms. And I would hop over to a sub n, and then what would the next one be? A sub n plus 1, comma, dot, dot, dot. Would you agree?
Yeah.
That means this one has to be smaller than this one, or equal. So how do we check that out? Well, what we're going to do, and we are going to disregard the alternating, because we're saying it's alternating here. So that's going to be n plus 1 to the 4th over 4 to the n plus 1 has to be less than or equal to n to the 4th over 4 to the n. All right, so how do we know whether that's true or not? Well,
Can we just plug and play and see what happens or not?
yeah, sure. I mean, we could put in a big number.
You can use the ratio test, right?
Well,
You're not doing like a series.
The truth of the matter is that this is 4 to the n times 4, right? Because if you were to bust this up, this is to 4 to the 1st. Right? So this denominator is bigger. Everybody agree with that?
Yeah. Yeah.
Yeah.
Mm-hmm. Oops.
Yes.
So if this 1 over 10 is going to be smaller than 1 over 9.
Yeah.
And then if you were to expand this, the highest exponent, this is going to be is oh my gosh, if I use Pascal, it'd be n to the 4th plus 4n cubed plus 6n squared plus 4n plus 1, I think. I think it's 1, 4, 6, 4, 1.
That sounds about. Well, there's a formula for the coefficients. We talked about that in high school.
There's like a triangle thing.
Yeah, Pascal's triangle.
Yeah, it's this, you know.
Oh, jeez. Remember
It's
that?
been a long time ago. I know. I would say it. You know, most of the time, and this is going to be smaller or equal to. Now I'm going to go to Desmos because Desmos is amazing.
True.
You'll see my screen.
She loves Transformers. Miss Muller, what car do you drive?
Bumblebee.
Yes.
Oh, what?
She legitimately drives Bumblebee.
Bumblebee?
Like the car. It looks just like it. Oh, yeah.
And I have Transformers all over. It's very nice. All right. So, you see my screen?
Yeah.
All right. What I'm going to do is cheat a little bit here to prove to you that it work. Oop. Try again. I don't type very fast either. That's another bad thing of mine.
Wait, what about that needs to be an X? Yeah, that needs to be an X.
There we go. There it is. There's that one. Okay, and then I'm going to say minus. Why did I do minus? I'm moving this over. If I move this over, this is going to be 0 over here. I'll show you in a second. I'm sorry, I realize you can't see that part. Sabin is texting me. You would appreciate that.
Well, what is Sabin saying?
He's me about worried about the students.
Oh.
Okay. All right. So is this always less than 0? It's looking like it's always negative, doesn't it?
Yeah.
Is it?
Yeah, it is. I'm pretty sure it is. I mean, we could really zoom in, but.
Well, just if you click on the graph, it'll tell you what the Y value is.
There we go. I like that.
Yeah,
Oh.
so it says the value is 0 there, so you probably have to go to 2.
Well, okay, right, because only, yeah. So 0 negative or 0 positive?
Right.
It's negative. I'm sure it's negative. There it is. See it?
Yeah. Perfect.
Okay, hold on. I need this one here. So this is true. So that one converges by the alternating series test because these two conditions are true. Now, most of the time, they're easier than this one.
Okay.
And if I was giving a final or a test, I'd make it easier. But of course, I'm not a college professor, but you know.
I had a question about that less than or equal to condition.
Yes.
What would happen if the terms were equal? Because if they're equal, it's not decreasing or increasing. So why would it be convergent?
I don't really have a good answer for you. I don't see very many series. In fact, I can't think of one.
Because the limit has to be 0.
Where it was equal.
It's okay.
Yeah, I can't think of one where I've had them equal. And if they are equal, they may be equal in the first couple of terms, but as you go further on, they aren't. Does that make sense?
So if it fails one of those though, then you have to go on and use a different test to be able to.
Right.
You can't just assume diverges.
Right.
Okay, so basically for any of these, if it doesn't prove exactly what we're trying to get, we can't assume anything. You have to try something else.
Right.
Right? Okay.
But how long is this test? Let me ask you.
2 hours.
The final?
2 hours. So they're only going to, and they're going to do all of series on this test? Is it just a series test or is it going to be everything?
It's like, I think he said what, like
50%.
Like half the test is guaranteed series because we haven't had a test on that.
And then the other stuff.
But the other stuff is
Pretty easy.
Yeah.
Pretty easy.
The other stuff we all have like good grasps on.
Right, but okay, right. So, but what I was trying to get at is I'm not sure I would give you an alternating series that wouldn't pass the alternating series test on a less than a 2-hour test.
Yeah, because we don't have enough time to.
Right. Well, unless this professor is, not very nice, and I don't know those kind of things. But if, I was testing whether you knew it. You could. The other thing too is that if it fails one of these two, and you could say, oh, okay, well, I have to test another test. I have to use another test. But it doesn't permit me to do that, but I know that I have to. At least you could.
Gotcha.
Well, the nice thing is we know the setup is going to be like 3 or 4 partial credit, and then the rest is multiple choice. So for something like this would have to be like a partial credit, right?
Right. Or if it's multiple choice, you might have to, do your best guess on the one that was alternating. You know what I'm saying?
I guess the multiple choice is gonna be more of the earlier stuff, and the
Right. And
the
redo
series.
Some, maybe one old one.
Yeah.
Maybe.
Yeah.
and I don't know if, yeah. So I would just let go of that. You know what I'm saying?
Yep.
But you're right. If it was on a free response kind of question, not multiple choice, I would suggest if one of these two fails, I would say, oh, well, I realize that we must try another test,
Yeah.
and then just go on.
Okay.
All right. So, let's see, what was next? That was 11. So
that's all the tests pretty much.
Did we all know the ratio test?
That's pretty simple.
Or do we want to?
Yeah.
Do you want to go over one real quick?
Can we go over
Yeah. Can we do one with the ratio test?
yeah, that would be number 9, actually. That was my, sorry, my son.
It's okay.
He's so funny. He said, oh, you should do these YouTube videos. Everyone would love you. I'm like, well, we'll see.
Well, yeah.
So most of the time when you see factorial, are you thinking ratio test?
Oh yeah. And then also,
Yes, absolutely.
because or at least I know that I didn't really know what a factorial was really
Right.
at all. And then my teacher kind of didn't really tell us what a factorial is. So I think I got it, but.
All right. Let's do number 9, and I'll talk about what a factorial is first. A factorial, like if I have an exclamation mark here, that means
5 times 4 times 3 times 2
right.
times 1.
I was going to say 5 really loud, but no, wasn't going to go over well, right?
I would have jumped.
Anyway, all right, but by definition, 0 factorial. Now this means by definition. If you have 3 equal signs is 1, because if you had a 0 here at the end, it would wipe everything out. And then why have factorial? Okay, so mathematicians said we're going to define 0 factorial as 1. Okay, so another thing important to know is n factorial is equal to n times n plus or minus 1, right? Because how do we get from 5 to 4? We subtract an integer 1 times n minus 2 times n minus 3 ... right? And then n plus 1 factorial is going to be n plus 1. Now, what's the next term after n plus 1? You subtract 1 and you get
n
times n minus 1, and you can keep going. Got it? And another way to write this is n plus 1 times n factorial, right? Because this could be n factorial. So those are the kind of things you might need to know for what we're going to do here with the ratio test, okay?
Gotcha.
All right, so I'm going to do this number 9 here. All right. Now, I heard someone in the background say, well, how would I know whether to use the ratio test? Whenever you have factorials, it's best to use the ratio test. Okay? All right, so let's write number 9 down here. That's the sum from n equals 0 to infinity of -1 to the n pi to the 2n over 2n factorial. Okay, using the ratio test. Now the ratio test, back when you're using series, or geometric sequences, R is equal to A sub n plus 1 over A sub n. You know, like if it's going to behave geometrically, like a geometric series or sequence is 2, 4, 8, 16, 32, 64. And how do you figure out what R is? Well, you just take the second term and divide it by the first, the third term and divide it by the second. That's all you're doing here.
Yeah.
All right, so that's going to be the limit then as n goes to infinity of the absolute value of A sub n plus 1 over A sub n, which is, this is basically R. All right, so let's do that. We'll say the limit then as n goes to infinity of, in this case, it's the absolute value of pi to the 2, and you have to go n plus 1 here in parentheses, right? Because you're replacing the n with the n plus 1 all over 2 times n plus 1 factorial over pi to the 2n over 2n factorial. Now that's really messy because it's a double-decker fraction and nobody likes double-decker fractions. So what I'm going to do is I'm going to keep change flip and say, and then I'm going to distribute this, okay? So we're going to get pi to the 2n plus 2 over, this is 2n plus 2 factorial times, and then this 2n factorial goes on top, which is really convenient because we're going to be able to cancel something out, over pi to the 2n. And here we go, the limit as n goes to infinity. All right, so when I have pi to the 2n plus 2, I can cancel the 2n parts. Do you agree?
Yes.
Because this is pi to the 2n plus 2 is pi times 2n times pi squared, right? Because you would add the exponents.
Yeah.
So then on top we have pi squared. And then this right here is in disguise 2n plus 2 times 2n plus 1 times what? 2n factorial, right?
Yes.
And you always break up the one that's bigger because you want to get the one that's smaller to cancel out. This was bigger, so this is the one you're going to break down. Okay, so I'm going to cancel that out with this. And on top, I've left with pi squared over 2n plus 2 times 2n plus 1.
Yeah.
And then the limit as this goes to infinity. Here we go. What's the degree of the numerator? Well, it's just 1.
Yeah.
Because there is no n up
zero?
here. Well, 0. You're
Isn't
right.
it?
You're right because
Yeah.
it is 0. It's 0 because there is no n up here. And the degree of the bottom here is 2. So this limit goes to 0. Therefore, this converges because for the ratio test, the limit as n goes to infinity of absolute value of a sub n plus 1 over a sub n. If it equals 1, it's sadly what? Inconclusive. Inconclusive. If it's less than 1, it converges.
Yes.
Just like the root test. And if it's greater than 1, it will diverge. So this case, what happens? It's equal to 0, therefore it converges.
Yep.
That makes sense?
Yeah.
All right. Oop, I was gonna see here.
Now that we've
Yes.
gone over all the tests.
Yes, sir.
I know how specifically to do it with the ratio test, but with all the tests in general, how would you determine the interval and radii of convergence?
Okay, well, for that, okay, so intervals of convergence and radius of convergence apply to a power series, which is like a polynomial that goes on forever.
Yeah, that's in the next section. There should be some examples from.
I would love to do those. Yes.
Yeah, the next picture I sent you.
Yep, I got it.
The next section after this was power. It's called power series.
Okay. The good news is that you always start off with the ratio test.
Yeah, and I like that one.
Right, that makes sense. Okay.
Right. Okay. So I'm going to go to my new page. All right. So do you want to start with, there are 3 possibilities. Okay. Should I give you the 3 possibilities?
This is 11.8.
So that's page 791.
So that was number 8 she was doing? Okay.
11.8. Power series. There are 3 possibilities for convergence. Now, I am an engineer. I am not necessarily a mathematician. Okay, so I'm giving you the bullet points and not saying if blah 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 blah, right? Very formalized definition.
That is, our teacher is very much a mathematician, and all of that language is what confuses our class.
No.
The way you're going to let us actually think about this in a logical way.
Well,
yeah,
that's what I'm all about. So if you don't have like the flowery theorem language, I'm giving you the nuts and bolts.
Yes,
okay?
Which is what that is what we've been looking for the entire semester.
Right. Okay. So the possibilities for convergence of a power series are, you have 3 possibilities.
Mm-hmm.
You can converge. Can I spell converge? Over an interval, like absolute value of x minus a is less than r. I'm going to call it big R for radius of convergence. Okay, where A is the center. Okay, so this would be over an interval. You would have an interval of convergence, right? Like, I don't know, an example like -1 to 1. Okay, you might have a limited area where you converge. You can also converge for all real numbers. That means if you were to use all of the terms in the series, it would converge and match the function. A very good case of that is e to the x and sine x, because they converge for all real numbers. They're power series. Okay, and or you converge at a point. Okay, and that would be the point of tangency or at the center. Okay, so at a point only. Okay, so those are the 3 possibilities. You can do it over an interval, you can do it for all real numbers, or at a point only. And and what do I mean by that? Let's say I have a function here, and you see how the tangent line shares the same function value, doesn't it, as your function?
Yeah.
Well, let's say you had a tangent parabola, which is what power series is all about. It only converges only at that point. You have a tangent cubic, it would only converge at that point. That's what I'm talking about versus an interval. All right, so We're going to do number 3, which is the sum of n equals 1 to infinity of -1 to the n, n x to the n. I'm sorry?
That's problem 3 in section 8?
Yes, sir. Yeah, it's 11-8, I believe. Yeah. I just figured we'd start with an easy one first.
Right,
Yes.
yeah, I just want to make sure I know what problem it was.
Good.
Yep. Okay, so when you're trying to find where a power, what makes this a power series is you see you have an x in here. Whereas when we look at this one here, do you have an X in here? You don't, do you?
Oh, okay.
Okay, because this is just a regular ordinary series, and this is going to be a polynomial if you were to expand it out. You know,
Yeah.
like if I let n equal 1, this would be negative, because that would be to the first, negative x, and then you'd go plus 2x to the second minus 3x to the third. That's going to be a polynomial. That's what makes it a power series, because it's a it's like x to the n. I'm sorry, what?
So if we see an X, because series, the letter is N. So if we see an X, then we do this.
Well, especially if it's asking for intervals of convergence.
Yeah.
Okay, so, and the good news is there's only one thing to do. I love that. The only thing to do is a ratio test.
Okay.
Okay, so using the ratio test, because you're going to try to find out where it converges, and the ratio test will give you the ratio as to when you get that to 1 and -1, and I'll explain here in a second.
No, for the ratio test, is it the absolute value of
It
the
sure
ratio?
is. Yep. So it doesn't matter about this.
How many points for talking about the absolute value?
No, it's always absolute value.
It is. Now, some books don't show.
Our teacher grades things weird. Our teacher grades things weird and like
took off points
wrong.
For using the absolute value instead of doing it twice.
Okay, so if that's the case, you don't have to use the absolute value. You just get rid of this.
Okay.
Because I don't know if Stuart might not use absolute value bars, but I bet you Stuart doesn't use this part. It won't.
No,
if you looked up
the teacher.
Oh, the does?
All
Teacher
right.
does? Oh yeah, okay. Well, I was going to say that's smart. But I'm biased. Okay. All right, so here we go. Remember, that's a sub n plus 1 over a sub n. And so let's do that. The limit as n goes to infinity of, now that means I'm going to put n plus 1 in here, disregarding the negative alternating piece. So that would be absolute value of n plus 1, x to the n plus 1 over n times x to the n. And I don't have to keep changing flip here because I don't have a double-decker fraction. And so we say then that the limit as n goes to infinity of the absolute value of, now I'm going to separate these things out. This is n plus 1 over n. Now what happens here? I can cancel x to the n's out, right? And then I'm just left with x. Are you okay with that?
Yeah.
Yeah.
Because this is x to the n times x to the first over x to the n, right? And that cancel those out.
Yep.
The hardest part about calculus is the pre-cal and all that you forgot. I know. Now, what's really cool about this in a power series is this is the limit as n goes to infinity, which makes this a constant.
Oh.
Because this doesn't care about x. This limit just cares about n. Okay, so what is the degree of the numerator here? If I made n a very large number, it would be 1,000,000 over a million, because this one says I'm insignificant.
Yeah, so it's just 1.
It's 1 times
X.
So this is equal to the absolute value of x.
Got it.
Now that's some magic, I know, but this is r. This is r. So what does that mean? That means absolute value of r has to be less than 1.
Which means that
convergence, absolute value of x has to be less than 1, which means x has to lie between 1 and -1. And so your interval of convergence, I like to call it the TIE fighter here. -1 to 1.
I love it.
And what's the center? 0.
Yeah.
So the IOC here is -1 to 1. And this is the radius of convergence, because if you were to complete the TIE fighter, it would look like a circle.
Mm-hmm.
So the radius of
Got it.
convergence is equal to 1.
And then how do you tell if it should be open or closed brackets?
You got to test the endpoints. Now, what does that mean? Okay, so let's test the endpoints, which is annoying. All right, so this is case 1, though. Do you see how it's case 1?
Yeah.
Okay, all right. Testing the endpoints.
Yes.
Now, what do you do to test the endpoints? Well, what are the endpoints of this interval of convergence? Well, it's -1 and 1. So I'm going to say x equals -1. That's an endpoint. And so I take -1 and I plug it into my, let's go back up to this piece of paper here. Up here. Okay, so going to my original series, that's going to be n equals 1 to infinity, -1 to the n, and I'm going to make this -1 here, right? Because I'm going to let x equal -1 to the n. Now, what's fascinating about this is I can simplify this a bit and say this is n equals 1 to infinity. What happens when you have the same base?
Oh.
So it's to 2n.
That's
Yeah.
right. You add exponents. You're right. So this would be -1 to the n plus n, which is 2n, right?
Yeah.
Times n. Now let's talk about -1 to the 2n. What kind of number is 2n? Even or odd?
Even.
Even.
It's even. So when I raise a negative number to an even number, it's always
Positive.
positive. So then this is going to be n equals 1 to infinity of n here. Okay?
And
Now, I have to use one of those obnoxious 10 tests that you guys all love. And what's interesting about n as n goes from 1 to infinity, is it getting bigger?
yeah.
So we're going to use the nth term test for,
Divergence.
yes. And what is that? That means if I take the limit then as n goes to infinity of n, that goes to infinity, which, what does that mean? That means
Means the divergence.
because it's different than 0. I should say diverges, not divergence. So it diverges at this endpoint. So what do we have to do now? We have to check the other endpoints. I'm going to go over here. What's the other endpoint on our TIE fighter? It's 1. So what do? We take that 1 and we plug it back in our original. So that's going to be the sum from n equals 1 to infinity of -1 to the n times 1 to the n.
Uh-huh.
All right. 1 to the n is easy. It's just, let's think about what, it's just 1. So this is -1 to the n times n, I'm sorry.
Yeah.
Now I'm going to use the nth term test for divergence on this one too. Well, because this limit does not exist. Let's talk about that. I don't know. You know what? I got to refresh my memory. Let me look at my book here real quick.
That's part of the test for divergence. If the limit doesn't exist, then it is divergent. Right?
Yes, it's going to diverge because it infinitely oscillates, right? Because it's going to, because if you were to expand this, you'd get -1 plus 1 minus 1 plus 1, right? So it's going to oscillate between -1 and 0. I just don't know if the nth term test for divergence, I'm having a brain fart this hour of night, whether it is, has to be positive numbers, you know? But the alternating series would blow up, you know, because the first condition on the alternating series test is, does the limit go to 0? Well, no, it doesn't.
Yeah.
So,
in the book, it says the test for divergence, if the limit as n goes to infinity of a sub n does not exist, or if it does not equal 0, then the series is divergent.
right. Does it say though, does the a sub n have to be positive? That's what I want to know. Can it be alternate? You know what I'm saying?
Yeah.
Hold on. I'm looking mine up.
I'm not sure that it has to be positive.
No, it doesn't. It doesn't state that it does. It doesn't.
Yeah.
Yep. No, and it would say it would have to be positive, right? That would be one of the conditions. I just wanted to make sure I wasn't telling you guys a lie. Because I am a Catholic high school teacher, you know?
Yeah.
So I would say that the limit does not exist. Because it oscillates between two numbers. Okay, so if that's the case, that means that our IOC is still -1 to 1. Okay, open.
Yeah.
If we would have got that the nth term test for divergence, one of them would have equaled 0, then we would have had to use even another test.
Yeah, you have to use a different one, yeah.
Okay.
Because the nth term test for divergence only tests for divergence.
Yeah.
It does not test for convergence.
Yeah.
Which is annoying, I know.
Gotcha.
All right, let's see here. Number 4. I don't know if there's any of in here. This one is converge. I think this one will converge. Oh, this one's an interesting one. 8 is interesting. Oh, I like 7. We should try 7 because this is e to the x. Did you guys know that was e to the x?
Yeah.
Yes.
What?
That's it.
That's e to the x represented as a power series.
That's that chart.
That's in the table that we were supposed to know. Yes.
Which page is that on again? That's
So,
Maclaurin series,
I think it's
right?
8.
Yeah, that's a Maclaurin series. A Maclaurin is a Taylor series centered at 0. So this one's centered at 0 because it's not got an x minus something. It's not transformed.
Right.
yeah.
That's it. Yes. All right.
So
Let's do number 7.
Yeah.
Oh, I'm sorry, go ahead.
Is there any tricks to like memorizing all of these, or do you just kind of gotta memorize?
Okay, so like cosine, you notice how they're even powers.
Yeah,
I don't know if you have the list in front of you. Do you have the list in front of you?
I do.
Okay, so you notice that the cosine are the even powers. Like the cosine series is 1, right? Minus x squared over 2 factorial
Yes.
plus x to the 4th over 4 factorial minus
X to the 6.
x. Do you see how they're all even even exponents?
Yeah.
And then the general term is -1 to the n x to the 2n over 2n factorial.
Yeah.
Cosine is an even function. Cosine is an even function because it's got symmetry with respect to the y-axis. That's how I memorize that one. And sine has odd symmetry, and it has those odd exponents. So it's x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, right?
How many clutch?
So I think about the symmetry.
Sorry, can you say that one more time?
Okay, so like cosine, if I were to draw it, it has even symmetry with respect to the y-axis. And the power series is got only even exponents, which somehow resonates to me. I don't know. And then sine
Whereas
is
sine,
a function because
sine is an odd function.
it's a symmetrical with respect to origin.
Oh.
And so that's what helps me memorize those two. And then e to the x is just, I don't know, that one, I don't really have anything easy for that one, but.
Well, it's x over n factorial, right? Pretty simple.
It's what? Yeah, that's that one.
Just x to the n over n factorial. That's not so bad.
Right. No, right, it isn't. And then this is another one of my favorites because this one looks like a sub 1 over 1 minus r, which is the sum of an infinite geometric series. And so what is a sub 1 here? It's 1, right?
Yeah.
And then what's r? X. So that's going to be 1 plus x squared plus x cubed plus x to the 4, right? So that's how I kind of see how this is r, and a sub 1 is 1. And what's r? I multiply it by x every time. I don't know if that helps. Yes, no, maybe?
Yeah, it helps. Yeah.
Okay. All right, so let's do number 7 because it's best to do an example of all 3 of these conditions here where you converge over an interval, which we did in one just now, where you converge for all real numbers and then you converge at a point. So you know what it feels like when you see it. Because on my series test in high school, I give them one of each. So they know that that's coming. So, yeah, you know, you're going to have to prove to me you know which one each one looks like. So, all right.
Miss Muller?
And then, yes, ma'am.
We're wondering, can you send us like some of the example problems you use on your tests for us to practice?
Sure.
Okay.
Sure.
So if you text that to me, I'll give that.
You have access to my Moodle. Did you know that?
For even the class that I wasn't in?
Yes, here, I'm going to show you. I'm going to minimize this. You'll see my screen, right?
Do I still have my Moodle from high school?
Oh, just relax. Watch. Magic will about to happen.
Okay.
I'm going to go to Moodle. You just need to have the Moodle. So it's moodle.btcatholic.org. Got it?
Yeah, I remember that website.
Okay, so you see there's this magic key right here that says.
Oh, as a guest. I see.
Okay, so we're gonna log in as a guest. Go ahead, log in as a guest. I'm clicking it. I'm gonna show you how it works.
Okay.
And obviously it's math, right?
Yeah. So I think everybody in here. Yeah. So all of y'all can go to this and see her test stuff.
Okay, so I'm gonna click on I'm gonna click on my BC class this year.
Yeah.
I'm clicking on it. All right, and there it is. Okay, so you guys might want to see my series. Oops, that's first semester. This is my infinite series here, right here. So I have a video on Introduction to Taylor series. And I have, let's see, my power series day 1. That looks like.
I'll get to this. You guys can all
There you go.
How?
You just go to
my note.
It's Moodle, yeah. The normal Moodle
btcatholic.org.
BT Catholic, which was like my high school .org, and then you log in as guest and you go to her page.
.org, yes. Okay, and I have a video on Introduction to Taylor series. I have one for, and you have my 17 BC test and my solutions worked out.
Gosh, okay.
So here's my BC test from 2017, which happened to be the same test I gave in 2018.
Can you ask her about
Anyways,
It's the same test.
Okay.
Oh, yeah. Go
Is it 2017, 18, and 18, 19?
to the 18.
well, you can go to either class. That's fine. But the 18, 19 is what I'm working on now. But I have them all worked out. You see?
That's
Okay.
fantastic.
Yeah.
I love you 3000.
So then we can all access. Perfect.
Yeah. And this one here, you can see how I use the ratio test. I actually test the endpoints. And you can see where I have one where it converges with alternating harmonic.
Yes.
And then this one here, Siri thought I was talking to her again. This uses the alternating series test, and I use the integral test on one endpoint.
Mm-hmm.
And this is at a point. It only converges when x is 0. And you see how I put the 1 over n at square root of ln on my test? That's a good one.
Yeah. Oh, yeah. Okay. We did one like that.
Yeah. And then this is the end-term test for divergence. This is the limit comparison test, which happens to be my favorite. Now, how did I choose that one? Because I wish that one wasn't there.
Yeah.
So, and then I had I had a free response, and then I had a calculator section where I made them come up with a Taylor series using their calculator, because our calculators, Mackenzie, can do Taylor series.
Oh, yes.
So, but anyway.
Wait, can you pause that for a second? Our calculators can do those?
We had to get the 89 for our
Will
class.
these expire?
You and I.
Yeah, but we can't use calculators in the final.
Oh, damn it.
Which
Yeah.
is a bummer.
Yeah, that's sad.
3, let's see. Do I have all the chapter 10 homework in here? Anyway, so, and then I have parametrics and polars in there too.
Yeah, and those are on our.
And then if you, I'm going to go back. And what you don't see there, you can go to the BC 2018, and you can see what I posted for them, which will be very similar, probably.
Okay.
And you can subscribe to my channel, Amy Muller.
This is YouTube?
Yeah, and it's just Muller.
It's Amy Muller?
Mm-hmm.
Mm-hmm.
She's my YouTube real quick.
Video on testing endpoints, convergence endpoints. I'm going to pull this up here.
Amy flowchart and no E, M-U?
Yeah, Muller.
That,
Oh,
it's like you mull around.
I got it.
Oh yeah, and look, there's you teaching math.
Right. See? This is a video where you test the endpoint.
Yeah, if you search it, then it says my name and we're live now.
Yes, we are.
Hmm?
We are live to
Yeah.
the universe.
Yes. Yeah, so Creighton, you can watch everything
Thank
that
you,
you
God.
talked about before we came in.
Oh, it's gonna be.
Oh, it's all gonna be.
Yeah,
Yeah.
it's here, it saves.
This whole
Yeah.
thing. And this is then.
Yeah, and then we haven't even gotten to like the
my-
Taylor
my
McLaurin
entire
stuff.
class.
Okay,
When is your test?
Thursday
At 1:11.
morning at like 11:15 on Thursday.
Oh, wow. Okay.
So-
Great. So let's do, can we do number 7?
Yes.
Yeah, we can.
I might just have if I could watch the whole,
Yeah, that's fine.
because I've been here since.
That's fine.
This is so-
Yeah.
All right.
So if we want to find the radius of convergence, the interval of conversion, we're going to use the ratio test. Okay, so that's going to be the limit as n goes to infinity of absolute value of a sub n plus 1 over a sub n. So let's do that. The limit as n goes to infinity of absolute value of that's going to be x to the n plus 1 over n plus 1 factorial. Now, a lot of times I'm just going to flip it right away if you're okay with that.
Yeah, that's fine.
N factorial over x to the n. Limit as n Goes to infinity. What cancels out here? The x to the n and the n?
Yes.
And then what do I do with this, Mackenzie? Because this one's bigger.
It's n plus 1 times n factorial.
Yes, ma'am. And then the n factorials cancel.
Cancel.
And then we're left with x over n plus 1, right?
Yeah.
And then,
And that's all it's.
and then, yes, this is 0 because remember the x is a constant because this limit only applies to the n.
Yes.
So this is 0. Well, on the ratio test, we had 3
Convergent.
conditions. Right, what was our ratio test? If it was less than 1,
Then it converges.
Converges, that's right. Right here, remember I did my little brownie face. If it was equal to 1, but that we don't have that here. And this one's less than 1. So does it even matter what x is?
No.
No. So therefore, this converges negative infinity to infinity for all real numbers.
Yep.
And so if I were to do the TIE fighter, I would say negative infinity to infinity, and the center is 0.
So then the radius is also infinity.
That's right. The radius is infinity.
Okay.
I have a question, if you don't mind.
No, fine.
All right. Is there an easier trick to do things like n factorial over n plus 1 factorial? Because I think sometimes when I do the ratio test, I get tripped up with that. Or
Like the canceling?
like n plus 1 factorial over n factorial, that kind of stuff, vice versa.
This is what I was showing a little bit ago. With n factorial, it's nothing more than, see, because 5 factorial is 5 times 4 times 3 times 2 times 1. And to get to the next number, what are we doing? We're subtracting 1 every time, aren't we?
Yeah.
Okay, so n factorial is nothing more than n times n minus 1 times n minus 2 times n minus 3, dot, 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 right? I could keep going, depending upon how large n was. N plus 1 factorial is n plus 1 times n minus 1. And I could keep going on here too. But what's interesting is n plus 1 factorial has an n factorial in disguise in it. You see that? Because this right here is n factorial. You see? Because you have n plus 1 times n minus 1, which turns out to be, this is n factorial.
So if I have something like n plus 1 factorial over n factorial, it's just n plus 1?
It is.
Okay.
And I did one just a second ago here, where let's say it's not n plus 1 factorial, but it's 2n plus 2 factorial. Right? 2n plus 2. I always choose the biggest one because that's the one that's going to break down the easiest.
Gotcha.
So the bigger one's going to have the 2n factorial embedded in it. So 2n plus 2 factorial is equal to 2n plus 2. And then I subtract 1 and get 2n plus 1. And then I get 2n factorial. And then so the 2n's factorials cancel, and I'm left with just these two terms. Or those two factors. I'm sorry.
Please let her know we're hiring.
What?
He said, please let her know that we would like to hire her here.
Oh, gosh.
Please.
My son keeps telling me I should teach at a college level, but I'd have to get a master's or a PhD because they don't let little, pipsqueaks like me do.
I hardly would consider you a pipsqueak.
You guys are very sweet, but I'm only an electrical engineer, so
You just said I'm only an electrical engineer. Oh my gosh.
You're very kind. Okay, so we did one where the radius converges.
And case 2.
All right, so now we need to find a case 3, which I suspect will be, let's see here.
Look at her. She just eyeballs this and figures it out.
know. I love your grammar.
I know.
Did your grandma die?
Yes, Miss Muller, I told them that you're virtually my grandma.
Oh, well, I love you for that. Because you cherish grandparents, so that's nice.
Yes, and they would all like you to adopt them as your grandchildren as well.
There we go. I don't have any yet, so.
I'll be your second.
Other than me. I'm your first.
Right, there you go. You're my first. The 8 is not going to be one of them. I might have to make one up. Oh, okay. 23. 23 is going to be one. Now, what leads me to that, do you suppose?
No idea.
Which one? 23?
Yeah.
That looks like a binomial series.
Well, right. Well, this looks like it's going to keep getting bigger and bigger and bigger, doesn't it?
Yeah, it does look like that.
All right, so let's try it. So we say the sum from n equals 1 to infinity of n factorial times 2x minus 1 to the n. And we're going to use the ratio test. Which is the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n, which is nothing more than r. So the limit then as n goes to infinity of absolute value of, we're going to have n plus 1 factorial times 2x minus 1 to the n plus 1 over n factorial times 2x minus 1 to the n. Now, I'm going to cancel the obvious thing first. This is the 2x minus 1 to the n goes away, and so does the n on top. And which one are we going to break down?
The n plus 1.
Yes, because that's bigger. All right, so that'll be n plus 1 times n factorial. It's got an n factorial embedded in it. And so I can cancel out the n factorials. And so then we have the limit as n goes to infinity of, excuse me, n plus 1 times 2x minus 1. Sorry, gotta get a glass of water here. All right, there we go. Now, what happens as n goes to infinity on this one?
It's infinity.
It is. Don't hesitate. You're right. It's infinity.
Yeah.
Because n keeps getting bigger and bigger and bigger. Now, it's not infinity at one case.
X equals 0.
X equals 1/2.
Yes, whenever this equals 0, it's not infinity. So this will converge only at x equals 1/2, which is the center
Okay.
of the, right here, of the TIE fighter, which the center is 1/2 here. But this doesn't even have any of this here, does it? Because it doesn't converge except right here. So the radius of convergence here is 0.
So, do you even have an interval, or is
No, it's just at a point.
So the only thing you can tell on this one is the radius, and that's 0.
Right, because it has no interval of convergence. It only converges at its point of the center, its tangency point.
Got it.
Okay. So I've done an example of each one of those.
Really quick, so
Yes. I'm
when
sorry.
you're saying
Go ahead.
when you get infinity times 0, you're saying that it's 0, and is
Okay.
that just your assuming? If you were to take L'Hopital's rules, then
Okay. The reason you don't have to use L'Hopital's rule here is that as n goes to infinity, the only thing that's going to infinity is this. This is not going to 0. Right? I mean, n plus 1 goes to infinity, but the only time this is going to be 0 is when x is 1/2. So if you use L'Hopital's rule, if n went to infinity, this goes to infinity and that goes to 0 at infinity.
Gotcha.
You know what I mean?
Yes.
Okay. They would have to be, doing the same thing at the same time. That's a great question. All right, so Taylor series?
Yeah, if we just do Taylor and Maclaurin, then I think we're
Do
good.
we know about 1111 and the applications of them? Because 1111 is.
That's special relativity. I don't know if we should tackle
11-1, that's going to be like changing a decimal into a series?
Oh, 1111.
No, we're talking about like the very last section. It goes with like
Taylor polynomials.
approximations.
Yeah, I like those.
I don't think I sent. Did I send you a picture like that? I don't know. Maybe I did. Let's see. Oh, I did. I sent you some from 1110 and 1111. So that's fine.
Okay, so I taught my son, and he's sending me really nice comments. That's really nice. About, yeah, you're pretty good at this. I'm like, well, thank you. All right, let's see here. 1110?
Yeah. That's the Taylor stuff.
that 11-9
So I wouldn't ask you any questions like 1 through 4. I'd probably ask you things like 5 on.
This is in section
1110.
1110.
Should we go over 11.9 first? Representations of functions as far as series?
Like how to do that?
Yeah, should we just do a couple of problems? Because this is
You didn't send me 11.9. Did you send me 11.9? You did not send me 11.9.
I did.
Do you need 11-9?
Yeah.
Yeah.
Okay.
We don't have to do a lot. Just like
Just a couple to make sure we know.
just like a general
Sure.
process of how we would take a function and make it into the power series.
Yes, absolutely. And I have a video on doing that. So, let's see. Creating power series from. I hope they don't take Moodle away from me next year. It's going to make me very sad.
You hope what? Oh, are they thinking about doing that?
Yes, they want me in a classroom, and I can't share a classroom with the world.
Yeah, classroom doesn't work for math, I don't think.
I don't either. Let's see here.
Okay, I just sent you 2 pictures with the work from 11.9. We probably only need one example of that, just like a general process of like what to do.
Maybe we could like do one for each case.
Are there multiple?
Yeah, because for the series, the case where one goes to a point or an interval or infinity.
I just did one. Of each of those.
Yeah.
Yes, I did one. I promise.
Okay.
You can rewind the tape. I'm not going to hide this tape from you.
Okay.
Okay. That would be like 3 through 10.
Yes.
Okay. Now, on 3 through 10, I would use series I already know. And if I were going to test you guys, I would not probably test you on anything but from 3 to 6. If I was going to give a test. Or 13 is a nice one. So I'm, oh, partial fractions.
That's good. You can do first.
So I'll let you decide. Or 15 through 13?
Yeah, why not?
13 is a nice
Yeah.
one.
15 or
yeah,
one of those
13
six.
seems like it like gives you the. Yeah, let's do 13.
You can still see the screen, right?
Yeah.
Yeah.
Sometimes I worry I'm going to disconnect. Okay, so it says use the differentiation to find a power series representation for this function. Okay, so this one looks like one that you might know. So go ahead.
The 1 plus 1 over x.
Right. Right.
Yeah.
So 1 over 1 plus x, right? That series is the alternating version of, right? So there's 1 minus x plus x squared minus x cubed plus dot, 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 plus negative 1 to the n, x to the n plus dot, 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 right? You agree with that?
Mm-hmm.
Yeah.
And that's the sum from n equals 0 to infinity of negative 1 to the n, x to the n. All right. So it kind of looks like this, and it says use differentiation. Well, what is the derivative with respect to x of 1 over x, or 1 plus x, sorry. Well, that's just, you're taking the derivative of 1 plus x to the negative 1, which is the derivative of this, right?
Mm-hmm.
So what, using the chain rule, what would that derivative be? It would be negative 1
1 over 1 plus
x
x squared.
quantity squared, right? Which is close, right?
Yeah.
So I can say that this series then, negative 1 over 1 plus x quantity squared, is going to equal negative 1 times this series. Do you agree with that? Right?
Oh.
Yeah, so I'm going to put negative 1 times, and I'm going to put this right here. So it'll be 1 minus x plus x squared minus x cubed plus dot, 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 plus negative 1 to the n, x to the n. Oops, I don't need a parentheses there. Plus dot, 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 right? And then, so let's multiply that in. That's going to be negative 1 plus x minus x squared plus x cubed.
So it's
Here. Go ahead.
it's basically just like if you just switch the sign and all the terms.
Well, hold on. No. Let's back up. I have to take the derivative of these, right? I'm sorry. Remember, what time is it? It's 11:02. I'm going back in time. We're rolling back the tape. There we go. None of you guys are laughing.
I'm laughing.
I just rolled back the tape. Okay. All right. So I have to take the derivative of all of these terms. Right?
Mm-hmm.
Let's do that.
Yeah.
Which is really easy. Remember, it's 11 o'clock. Okay, so I'm going to take the derivative of 1, which is, here, good, I like that.
Yeah.
And then we're at negative 1 plus
Okay.
2x minus 3x squared plus dot, 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 plus the derivative of negative 1 to the n is nothing, right? So I'm just going to leave it. It's a constant. It goes along for the ride. What's the derivative of this?
And x to the n minus 1.
Right. Plus dot, dot, dot.
Why?
Because you can do power down function, lower the power 1.
Power down.
Oh, okay.
Yep. Okay.
Right. All right, so if I were gonna write the, summation here, it's gonna be -1 to the something. I'm gonna figure that out in a minute. N x to the n minus 1. And so this is where we get a little bit crafty with our index of summation here. I need the first term to be negative. So if I make this 1 and I put an n here, this is a -1, right? Because -1 to the odd power is negative.
Mm-hmm.
And then if I put 1 here, that works. And then what happens if I put x to the 1 minus 1?
That's just 0, so that'd be 1.
That works, doesn't it?
Yeah.
And then let's bump the counter up to 2. So that would be -1 to the second, which is positive. I'm happy about that. And then and since it's 2, it's here. And then this will be x to the 2 minus 1. So it's working.
Works too.
So typically when you take the derivative, you change it from 0, you bump it up 1.
Okay.
But I don't take that in faith. I just check in my head to see if it matches.
Gotcha.
Okay.
So that would be like considered our f to the n derivative kind of thing.
I'm sorry, this is the general term?
So, it's like on our last quiz, we had to use like f.
We had to use like the value of the nth derivative at a.
Oh, yeah.
So like,
Is that like ahead of like? Does that come later?
Yes.
Then-
That's error. Yeah, that's error.
No, it was for the whole thing. Show her their formula.
That was like
it
the.
was f to the n
We're
times
doing,
your x minus a to the n
no, here's what
over
it is. We're
n
doing
factorial.
11.9 right now.
Yeah,
It's 11.
Yeah.
So
I think that's the never mind. That's the next section that involves Taylor
You're
series.
talking about the Lagrange form of the error. When you say x minus a to the n plus 1 over n plus 1 factorial, where you do the nth derivative of that. Anyway, I think.
Yeah, we're like a section ahead. Never mind. We're
So I
good.
said it normally goes from index 0 to 1. If the index was already 1, would it go to index 2?
Yes.
Okay. All right.
That's
So you
what I bump it up and then I test it, right? I just said I don't take it by faith. You see what I did?
Yeah.
I tested to make sure that it would match.
Yeah.
Like I would make n equal 1 just to make sure it equals the first term. Then I would let n equal 2 to make sure it equals the second term.
Yep.
Just to double check. All right, so part A says use differentiation to find a power series representation for this, which we did. Now, this one's interval of convergence is -1 to 1. Now, I make my students memorize this. This is the IOC for this one.
Okay.
The IOC for the derivative is always the same as the
Yeah.
parent, okay? So the radius of convergence here will be 1 because if you did the TIE fighter from -1 to 1, the center is 0 and R is 1. Okay, that's part A. Part B says use part A to find, wait. To find a power series, does that say to the third?
Yeah.
So what are we going to do again?
Same thing.
We're going to take the derivative of this one. God bless you.
Okay. So.
And what's the derivative of that? That's going to be, I got to rewrite it, -1 plus x quantity squared.
Isn't that -2?
Yeah, I'm sorry, yeah, -2. So it's
So
going to
then
be
it's-
2 over,
Or 1 plus x to the third. Yeah, cubed.
which is close.
Mm-hmm.
Can't you just take 2 times that series?
Well, no, because this is the derivative of this one. So what are we going to do? We're going to take I fell into the trap just a minute ago. 1 plus x cubed. What are we going to do? We take the derivative of all of these.
Yes. Yes.
So what's the derivative of -1?
0.
And then
2.
2 minus 6x.
6 plus.
This would be, what would this be? This would be 4x cubed, right?
Yeah.
which would be
12
12x squared.
x squared. Yeah.
Yep. Plus, plus, -1 to the n, and then the derivative of this is going to be power down again, so it would be n times n minus 1 x to the n minus
2.
2 plus
Yeah.
dot. And then if I were going to do a summation, well, I started this one at 1, I started this one at 0, I'm probably going to start this one at
2.
2. But we're going to check it
Gotcha.
out. -1 to the n times n minus 1 x to the n minus 2. Let's see if it works by letting the, can't see it, but here it is. So we're going to let n equal 2. What that's going to be, what kind of number? -1 to the second is positive, which makes me happy. And then I put a 2 here times 1, which is 2. And then x to the 2 minus 2 is x to the 0. So I that's positive in more ways than one. Okay. And then we let n equal 3. And then we let n equal 3, that's a negative number, which makes me happy. And then 3 times 2 is 6 x to the first. So is this working?
Yeah.
Yeah.
And so this one's IOC is the same thing.
The same as the
Yep.
parent, which is then still negative 1 to
And
1.
R equals 1.
So not every time are you going to be taking derivatives. Just for this case, we're taking derivatives because we noticed that if we took the derivative, it makes it look like one that we had.
Yes.
Well, and this problem also told us.
So for these kind of things, you kind of have to memorize that chart and then kind of be able to look at what one it looks similar to, and then kind of like be able to rearrange it to get it. Like I guess.
Right. I have a worksheet. It's called Creating Series from Other Known Series. I'm showing it right now on my screen. Where these are the ones, I'm going to make it bigger here. These are the ones that I make my students memorize. Okay. These are the classic ones. Okay. And so this one, number 1 looks like 1 over 1 minus x, right? Except what's
Yeah.
different? Different.
It's just 2 there's
So-
just a 2 in front of it.
I say, well, gosh, f of x, I'll say g is equal to this. And then, well, f of x is equal to g of 2 of x, which means I'm going to put 2x where the x is here. You see that? And then you just and then you just substitute it in, and you get your own Taylor series. Okay?
I got it.
So let's look at number 2 here. So what's the difference here? Well, it looks like I took the 1 over 1 minus x and substituted in what? X to the 4th. And then multiplied it all by x.
Oh.
See how that works?
Yeah.
So instead of x,
Right? And then I do it a step at a time because I have a article.
So it's just a
Uh-huh.
And this really should have an x here. I don't know. That's a typo. That says typo, not a typo, but it's a mistake on my part. This should have an x up here because it should match that. And then this one is cosine of 3x. What does that mean? I take 3x and put it inside cosine series.
Which looks
remember
like that, and
two,
then it's
why is
just
n plus- why is it 4n plus 1? Why is it x and 4n plus 1?
Because when I multiply the x in, when I multiply,
it raises the power of everything by 1.
right.
Okay.
This exponent here is 1.
Oh.
It's really cool how it all works. And then cosine 3x, you would just take where you see the x in the cosine series and you plug in 3x.
Yeah.
And
Oh my
this is
god.
like
Okay?
exact, but what's the title of this?
Creating series from
I call this is a really pardon the pun, powerful thing to be able to do.
Yeah, this is helpful. Okay.
Because why are we doing this? Well, can you help me remember? I'll remember. I'll minimize this. gonna go to this, pop this out. It'll let me pop it out. There's Desmos. And I want to look at this one. Why on earth do these power series things? Well, because if I have my function y equals 1 divided by 1 minus 2x, I can approximate it using a polynomial. What's the polynomial? It's 1, 2x, 4x second, plus X
what is that? X
cubed,
cubed.
right? Okay.
Yeah.
And of course, I'm so zoomed in here, it's ridiculous. So I'm going to zoom out again. Come on, come on, come on, come on. There it is.
Oh,
Over the interval of convergence, which is going to be negative 1/2 to 1/2 here because r is 2x.
yeah, yeah.
1/2 to 1/2, man, that's a perfect
Oh,
fit.
and like matches. I see.
That's where it's converging. And
Oh.
the interval of convergence is, we say x equals negative 1/2. Whoop, I type. The answer's no. To x equals 1 divided by 2. You see, over this interval where I have, I'm going to make this green so you can see it. And we'll make it dashed. Over this interval, if I add more and more terms, what is it, plus 16 to the fourth, better and better. And it's going to go better and better between negative 1/2 to 1/2, which is this interval of convergence.
Yeah.
And if I were to add infinitely many terms, it would be so good. You know, it'd be amazing. So, and why do we do it? Because by taking the derivative of these terms, it's so much easier than taking the derivative of this. Even though we can do the quotient rule or the chain rule with that, you know, but that's why we do it. Because there are some things you can't integrate, like, do I have one that we can't integrate? Inverse of x squared. That one. So you can take the antiderivative of all of these, you know, and you can't take the antiderivative of that one. So that's why we do it.
Yeah.
I don't know if that helps you.
That helps a ton. That worksheet helps. Yeah.
Yeah.
Yeah, that's great. I've got one question about the 11, 9, 13 that you were just working on from our book.
Yes.
Will that work?
Sure.
So how are you going from 2 over 1 plus x cubed to 2 minus 6x plus 12x squared? Where are those numbers coming from?
You're taking the derivative of the same thing you did in the first one.
Okay, so what I did was I took the derivative of this one.
Right.
Because the derivative of this is equal to this, right? Do you agree with that?
Yes.
Okay, so the derivative of this is equal to this. If I take the derivative of all of these terms, which is equal to that, then this is going to equal the derivative of all of these terms because this one's equal to this one.
Oh, is it 2 times the derivative of all those terms?
No, because the derivative of this here is 2 over that.
Oh, I see. So 2 is the derivative of the second term. Minus 6x is the derivative of the third term.
Yes.
Oh, okay, got it.
Yeah, and so this isn't this is creating power series from existing power series differentially, meaning you're taking the derivative multiple times to create. And the one that I just showed you, I was using substitution to create a series from another series. But here you can also take the derivative and create another series. You see how it's a little bit different? I'm not using substitution here where I use substitution on the other page that I was showing you.
Okay.
There are 2 ways, and you can create another series by integrating. Like I could take the antiderivative of this, and it would be the natural log of 1 plus x. and I could integrate all of these terms, and I would create its own series for natural log of 1 plus x.
So say we take the derivative of something and it comes and it like gets really close. Do we ever like were you gonna times by -1? Did you
No,
have
no. I was, because it's so late at night, I was going back to the where I created it by, substituting.
Well, because it wants 1 over 1 plus x squared, but we have like a negative 1 over 1 plus x squared, so we don't have to like times everything by -1, like the sheet
Yeah,
says.
so when we have the alternating series.
Oh, I see what you're saying. Yes. Yes. So we created, whoops, I'm sorry. Let me make this bigger. We created the series for the opposite of, we made this one right. So the answer to part A would, I'd have to multiply these all by -1. Yes, you're right.
So it would be 1 negative 2x.
Yes. Mhm.
Oh, okay, that's what my question was. So you
Yeah.
do, so since
Would that
it wanted the positive one, okay.
Yeah, okay. So I didn't follow this exactly. You're right. I should multiply this by the -1 to get the series for this one. Yes. And then
Okay,
this
and
one,
would that-
and this one, what would I have to do to this series? I'm sorry. This is this
then
series.
you have to take
I'd have to divide it by 2. Yeah.
okay.
Okay. So yeah, I'm sorry. I wasn't clear about that.
That's fine.
So
Thank you.
let's do 1 over 1 plus x quantity cubed to get it right. So what if I do that? What happens? We get 1 minus 3x plus 6x squared plus plus -1 to the n. And then I would have to do what to this? Divide by 2, right? Because I'm dividing it, right? Which is n times n minus 1 over 2, x to the n minus 2 plus ... So that would be the series for this one.
Okay.
And then this one here says, find it for x squared times that. So what would I do? I would take this one.
And then times it by x squared.
Yeah, but I'm going to do the series here. This would be 2, and this would be 1. I mean infinity. And then it would be n times n minus 1 over 2, x to the n minus 2. And then if I were multiplying it all by x squared, what would change?
You'd multiply everything by.
Yep. So that would be x squared minus 3x cubed plus 6x to the 5th plus ... plus -1.
Are you multiplying it by x squared or x cubed?
Oh no, am I?
I think you did x squared for the first one. Yeah, I think
Yeah,
that's
this is the 4th, right?
okay.
And then n times n minus 1 over 2. See what I'm saying by multiplying in public? I'm terrible. You're adding in public. This is going to be x to the. What happens now?
And
If I multiply by x squared, I'm adding 2, aren't I?
is that just x to the n?
Yes. Yeah.
No, it's the 4th
Why?
because you multiply it by x squared.
Wasn't it already 6x
Squared.
cubed though?
No, it was 6x squared and the one above
It
it.
was 6x
And I
squared.
made it 5th by accident. I was increasing my exponent by 1, which was silly.
Yeah. Okay.
So it's minus 12x5, right?
Yeah.
And you would recommend doing the derivative way if most of the time if we can, or it just kind of depends.
Well, if you notice that this is close to the derivative of this, absolutely,
Okay.
absolutely, I'd use differentiation.
And you said the different ways of doing it is integral, derivative, and what was the last one?
Substitution.
Substitution, where like if you have a series, you can substitute in.
Okay, got it.
Yeah.
It looks like. Okay.
Can you go back down to the bottom of that one sheet? right?
Sure. You bet.
There's x to the n, 1, right?
It's x to the n here because what am I doing? I'm multiplying by x squared, which means I'm going to add a 2 to the exponent here.
Oh, it was n minus 2 before, not n minus 1.
Yeah.
Yeah.
Okay. So times x
Yeah, and I apologize. This should really be times -1, but
We can
Um,
always find that when we check though.
yeah.
yeah, I'd be human.
Yeah.
That's an easy fix, yeah.
Okay, Miss Muller, it's really late and you have to get up and teach school tomorrow.
Yeah, thank you.
Do
very
you
much.
have time tomorrow to go over Taylor and McLaurin really fast?
Sure, probably.
Okay,
And I could
okay.
probably do it earlier. I'm just trying to, be healthy so I can live longer.
Yeah, that's fine. So just let me know whenever you're around tomorrow night, and we'll do the same thing that we just did today.
Thank you very much again.
Yep.
Yeah, thank you.
You got it. And I'm probably going to edit the first part of this video to get rid of all of the stuff that we did before.
All the technical difficulties before we knew what we were doing.
Yes.
Yes.
So give me a few minutes to do that, and then it should be available to you, okay?
Okay. Perfect. Thank
All right.
you.
Take care of yourself.
Thank you.
All right.
So helpful.
All right.
Okay, we'll see you tomorrow.
Sounds great.
Okay.
All right. Talk to you soon.
Bye.
Bye.
What?